Hello, Algebra 1. We are going to be on page 95 of the yellow book, page 95, the yellow. So this is called Piggies in the Pool. Now, I don't know what this really entails, but let's take a look. So problem number 1 on page 95 says, my little sister, Savannah, is 3 years old. She has a piggy bank that she wants to fill. Perhaps you have somewhere that you throw your spare change into. Might not be a piggy bank, might be a glass or a jar or something. She started with 5 pennies, and each day when I come home from school, she's excited when I give her 3 pennies that are left over from my lunch money. Use the table to graph the equation. Okay, so let's think about this. She starts out with 3 pennies. Okay. All right, take it back. She starts out with 5 pennies, and the older sister gives 3 pennies each day. So let's just mark this 0, 1, 2, 3, 4. That should be enough. So on the first day, there's 5 pennies. Or on day 0, she has 5 pennies she puts in there. And then the older sister gives her 3 pennies each day. So it looks like it's growing, right? Okay, so if we made the table, you could say pennies and F at P for pennies. So day 0, there's 5. And then day 1, there's 8. Day 2, there's 11. Day 3, there's 14. And it keeps going, right? And then let's take a look at the equations. So we could do our explicit. That would be next plus 3. And then remember, we have the 0 term, which is great. Okay, so that means we can just deal with, in this today, we're going to use P rather than N. Remember we were using N before? Well, let's use P now. So we're going to say F at P. So this is our recursive function. So F at P is equal to, it's growing by 3 each time. So it's 3 times P. And then the first day had 5. And there's our equation. Number 2 says, our family has a small pool for relaxing in the summer that holds 1,500 gallons of water. We decided to fill the pool over this for the summer. I was getting bored and just standing there watching the water flow, and began to think about mathematical model for the time it takes to fill the pool while we were waiting. I checked the flow on the hose and found that it was filling the pool at the rate of 2 gallons every minute. When I had 5 gallons of the pool is when I started the timer. Okay, so let's think about this. We have this pool, so when they started doing it, and we'll make water red, there was 5 gallons in there. That was the start. And then we had this hose that was coming in and putting water into the pool. And the water's going into the pool at 2 gallons every minute. Okay, so let's make our table. So maybe we'll do W and F at W for water. We'll use the W. So when we first came out, we were like, oh, there's 5 gallons in the pool. And then at the first minute, there would have been 7 gallons. In the second minute, there would have been 9 gallons. The third minute, there would have been 11 gallons. And it keeps going until we get the pool all full. Okay, so we graph this. And then label down here, we got 0, 1, 2, 3, and it keeps going. Okay, so at the very first time, we had 5 gallons. And then we realized every minute there was 2 more gallons. So that's what that looks like. So our recursive equation would be something like next plus 2. And then our explicit would have been F at W And this is good because we have the zero term, right? So we can just use W. We were using N before, but now we're going to use W. So I have, and it's increasing by 2 each time. So 2W plus our original 5. And that's our equation. On the next page, number 3, page 96, up at the top it reads, I'm more sophisticated than my little sister, so I save my money in a bank account, which pays me 3% interest on the money in the account at the end of each month. If I take my money out before the end of the month, I don't earn any interest for the month. I started my account with $50 that I got for my birthday. Use a table to graph the equation to create a mathematical model. Okay, so things that we know. 3% per month. And they started with $50 in the account. So let's make a table. So we're going to use M and F at M. M for money. So we started our account, we put $50 in. And then after the first month, these will be months, 2, 3, etc. So we're going to be increasing, we're going to be multiplying by 0.3. So we increase it each month times, if I just do 0.03, that's going to just tell me how much money I would have made. If I multiply by 1.03, that's going to tell me what it's going to do. So that's a big key there because we're growing. So I'm going to go 50 times 1.03. I'll use the calculator. And that's going to give me $51.50. I use 2 decimals because it's money. And then I'm going to take that and multiply that by 1.03. And then that's like 53.04. And times that again by 1.03. And then that's going to be, so this is at the second one. The third one is going to be 54.64 rounded up to the nearest penny. Okay, so if I graph this, I have to be kind of cautious how I graph. So I start at 0 and then 1, 2, 3, etc. And then because I'm up at 50, maybe I'll count by tens. Okay, so when I first started out, I had $50 in my account, which is right there. And then at the first month, I was at 51. And then I was at 53. I'm just kind of estimating this, and 54. Okay, so that's kind of our growth. Okay, because we have a multiplication here, this is going to change it from arithmetic to geometric. Okay, so our recursive will be next times 1.03. And being I have my 0, that's great. I'm just going to use M. We hadn't used N, but we're using N. M for now. So my explicit is going to be, remember this, we have F at M is equal to 50 times our growth factor, 1.03, and we're going to raise that to the M power. Okay, so this is geometric growth because we were doing a multiplication, not an addition. Okay. Number 4, at the end of the summer is on page 96, I decided to drain the 1,500-gallon pool. Okay, so their pool had 1,500 gallons. I think this went back with the other one. I noticed it drains faster when there is more water in the pool. That was interesting to me, so I decided to measure the rate at which it drains. I found that it was draining 3%, so there was this many gallons. It's going to decrease by 3% every minute, so we're decreasing. So that means every minute I have 97% left in there. So 97% as a decimal is 0.97. So we have to kind of keep that in mind, okay? If I go back to this problem, we grew by this 3%. 3% as a decimal is 0.03, right? And remember, we had to add 1 there. But in this case, we're going to have 97% of it, or 0.97. So if I did my water and F at W, okay, so at 0, there was 1,500 gallons, and then I'm going to go from there. Okay, we're going to have 97% of our water each minute. So I'm going to multiply by 0.97. So at the first minute, I have this many gallons. Second minute, I'm going to have this much. Third minute, I'm going to get 1369.0. Okay, and that's our gallons. Okay, so if we made our table is going to be harder to figure out because we're in the thousands, right? So we got 0, 1, 2, 3. So maybe we count by, I don't know, maybe by hundreds. 200, 300, 400, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so when I first started draining, it was at up here. After the first minute, we are at 1455. So it might have been here. Second minute was at 1411, so it's right here. Third minute, we're at 1369. So it's definitely going down, but we're multiplying. So we're multiplying each of these by 0.97. Okay, so my recursive is going to be something like next times 0.97. Okay, and my explicit, we're going to make it geometric because we're multiplying. We started with the 0 so that I can just use W. So I'm going to say F at W is equal to the 1,500 original gallons times our growth factor or our decay factor raised to the W. Okay, so number 6 on page 97, if we compare 1 and 2, so this was problem 1 and this was problem 2. So these were arithmetic. Okay, so they are growing at the same rate each month. For problem number 7, compare 3 and 4, we are either multiplying, so it's either increasing or it's decreasing. The number 4, the 1,500 gallons, is decreasing. Number 3, the your money is increasing. So when we do an increase, it's going to be the percent plus 1. And if we do a decrease, it's going to be 1 minus the percent. Okay, make the percent a decimal. Okay, so when they are increasing, they're called exponential functions. Linear are, so linear makes a straight line. Okay, it could go up or down, doesn't matter. If it's a straight line, it grows or shrinks same rate. If it's geometric, which they're now going to call exponential. So this is if you're adding or subtracting. If it's geometric, that means we're going to be multiplying. So growth is going to be 1 plus the percent, and decrease or decay, sometimes they call this decay, will be 1 minus the percent. All right, we're on page 96 or 98. It says about the middle of it. Oh, we're going to talk about the domain. So when you start talking about a domain, this is what's taking place on the x values. So a lot of times our domain in these particular problems you start at 0 in the x direction. Okay, so if we go back to our other problems, we go back to number 1, our domain is going to go from 0 to infinity. So we start at 0 and we go to infinity. We can also write that as x such that x is greater than or equal to 0. That could also be the domain. This vertical thing means such that. It's just a math term. Okay, our second problem is our domain. We start at 0. And I use a square bracket and go to infinity. Okay. In this case, it might be 0 to full pool, or you're flooding your yard. And then you could say that the domain is basically x such that x is greater than or equal to 0. And our domain here, it starts at 0 and goes to infinity, or the end of time. So you could say that x such that x is greater than or equal to 0. And then the last one, our domain, our x value would be from 0 to infinity. And notice I have a hard bracket, square bracket, because of our starting point. And so we could say that x such that x is greater than or equal to 0. These are all the domains of that. Okay, so so in the lesson we learned as possible units we call the domain. We found that some situations are best described using a discrete model, and others are represented better using a continuous model. Okay, so now we're talking about discrete or continuous. Excuse me. OUS. Okay, discrete means, you know, like each month, where you would just have dots. Continuous would be like the water. Okay, so continuous, even at the fraction of a second, we would use a line. We would connect our dots to a line. So if we had dots like this, for continuous, we would represent having a line there, or connecting the dots. Let's take a look at the retrieval. It says for each sequence, find the next 2 terms in the sequence and state whether the sequence is arithmetic or geometric or neither. Okay, so letter A on page 98, we have 4, 8, 16. So it looks like we're multiplying by 2. So that'd go to 32 and 64. And this would be geometric, which we called exponential. B, we have 2, 5, and 10. Well, that increased by 3, increased by 5. So that's changing. So that's going to be neither geometric or arithmetic. And letter C, we have 6, 9, 12. And it looks like here we're adding 3 each time. So this would be arithmetic. Okay, on page 99, it says find the unit of rate for each of the terms. A dozen ears of corn costs $5. So a dozen means 12. A dozen corn costs $5. So that means each dozen you add 5 to it. Okay, so this is our rate. Number 3 says 3 t-shirts for $10. So 3 t-shirts for $10. So that means we're going to add 10 to both sides. So that's kind of our rate. So this is like 3 for 10, This one would be 12.45. So this would be our rate. Number 4, solve each equation. So I have 7x equals 42. So what did I do to both sides? I divided both sides by 7. So x is going to equal 6. For problem number 5, we have 1/5 x equals 4. So we're going to multiply both sides by 5. Those cancel, so x equals 20. All right, so your homework for tonight, and you have the rest of the class to work on this, is going to be page 101 and 102. So take a look at that, give it a good shot, and we will take a look at that tomorrow. Have a nice day, everybody. Bye-bye. Bye-bye.